All right, we're now going to talk about Earth, the largest of the terrestrial planets, and by far the most interesting. It's the most dynamic, the most changing. Most of the other terrestrial planets, their surface hasn't changed in millions, hundreds of millions of years. The Earth is changing continuously. All right, a few numbers for you just for interest. The mass of the Earth is 6 times 10 to the 27th. That's grams, which is a huge number. The diameter is 12,756 kilometers. We've been talking about that. That makes it the largest terrestrial planet. Its density is 5.5 grams per cubic centimeter, which is similar to Venus and Mercury. Surface gravity we've already talked about is what we call 1G. And our rotation period is 23 hours and 56 minutes. We do 24 hours because we do it by the sun, but the sun, remember, is because we do a solar day and then we move slightly every day. All right, so this picture here of the Earth was taken by Apollo 15, I think, it's either 15 or 16, on their way back from the moon. And it's become kind of the iconic picture of the Earth. Most of the satellites that we have up there in the space station, all that, are in low Earth orbit. And so you never get a picture of the whole Earth. So you have to get far enough away where you can see the whole Earth like that, which is doesn't happen a lot. But look at the variety. All this is weather. These are clouds spinning off. These are low pressure zones right here. Through the middle of Africa. Africa is the desert here and has a desert on this side, but then you have the equatorial region in here, which is very wet. And you can see it's very changing in Earth. It would be a great place if you lived on another planet to watch, because every night it would change and you would see different things happening all the time. All right, first thing we talk about, well, before I get to that, we're going to talk about the atmosphere, but look at the atmosphere. We draw the atmosphere as this large object, but the truth is, it's a very thin layer. That thin little blue line right around the edge, that's the atmosphere of the Earth. So relative to the size of the Earth, our atmosphere is actually very thin. All right. So our atmosphere has multiple parts, and let's talk about the composition of it first too. So the atmosphere of the Earth is currently about 78% nitrogen, N2, about 21% oxygen, and about 1% of all kinds of other things. It includes water vapor, carbon dioxide, methane, some noble gases like argon, neon, all that's down there in the less than 1% range. So most of it's nitrogen and oxygen. This is not the way the atmosphere of the Earth always was. In fact, it's only been that way for the short time, geologically speaking. The primordial atmosphere, which is the original atmosphere of the Earth, was probably very similar to what we see on Venus, where it's 95% carbon dioxide, and then it has a few other things like nitrogen and other gases in it, but mostly it's all carbon dioxide. That's the way our atmosphere probably started. It occurs that way because this carbon dioxide molecule comes from all the outgassing. So remember, when it started, the whole Earth was molten, and a lot of that gas that ended up being in the atmosphere was gas released from all these rocks up into the atmosphere. Now, what changed our atmosphere from one that's mostly carbon dioxide to one that's mostly nitrogen and oxygen was plant life. That changed everything. We think, and nobody's exactly sure, but it seems like, as far as they can tell right now, that these single-cell plant-like organisms that could take in sunlight and nutrients and carbon dioxide and their waste product with oxygen, and they would grow and reproduce, they occurred very early, right when the Earth started to finally cool off. And that changed our atmosphere. Over billions of years, it took a long, long time, but over billions of years, they started converting this carbon dioxide into oxygen. And then you started getting animals that can convert these shelled animals, would take the carbon dioxide out of the atmosphere, and they would make it into their shells, but then those shells would end up on the bottom of the ocean, they get compressed, and they would make things like limestone, which is a type of rock, but it sucked carbon dioxide out of the atmosphere. And so all those things over time, it started to take the carbon dioxide out of the atmosphere, and now our carbon dioxide is a small percentage of our atmosphere, but it's going up. That's our biggest thing we're worried about. It's the greenhouse effect, which we talked about, is that carbon dioxide amount, even though it's a small percentage, affects significantly the weather on the Earth. So it was plant life, even single-cell organisms that changed the atmosphere of the Earth. Good for us. We can't survive in a carbon dioxide atmosphere. All higher forms of life, other than plants that are very mobile, very active, need to use oxygen or something like this. Is way more efficient than a carbon dioxide or plant uses. And so that's why we have a lot more energy, essentially. All right. So the layers of the atmosphere, we live in the troposphere, way down here. And notice the troposphere is from the surface of the Earth up to roughly, give or take, it depends on how you do this, in kilometers here. This is in 10 kilometers, which is about 10,000 meters, or about 40,000 feet. But the troposphere actually varies depending on where you are on the Earth. On places close, when you're closer to the equator, the troposphere is actually thicker and thinner in different areas. All right. One great thing about our atmosphere that saved us and why we're here is you see the water vapor and all the clouds? They go up here to the stratosphere, but they don't go above that. We have what we call a vapor barrier. That keeps our water from being lost into space. So we have the water cycle. The water evaporates, goes up, then it rains back down, and this continues all the time, but we never lost our water. Critical. Venus probably has as much water as we did, but they lost it. It's all gone. So it's critical for us. It kept the water. Also, you notice how the different layers here, these layers are done by temperature. As you leave the surface of the Earth, the temperature cools off. In fact, I notice that all the time because I fly a small airplane that I built, and there's no air conditioning. So you go fly in the summer, it's 100 degrees on the ground, you're burning up, but you get up to about 7,000 to 8,000 feet, and it's about 60, 70 degrees. You open the vents and it's very nice because there's no air conditioning in the small plane. So you want to fly higher in the summer to make it nice and cool. So as you go up, it gets colder and colder and colder here. This is in Kelvin temperature here. And then once you hit the stratosphere, it starts to warm up again. Okay? It starts to warm up because it's absorbing more radiation from the sun. And this layer up here, this is the ozone layer. Remember, ozone is oxygen 3. It's oxygen combined where you have 3 oxygen molecules together. Well, that ozone layer is important because it actually blocks the ultraviolet radiation that hurts us and makes us, gives you skin cancer and all kinds of bad things. So we need our ozone layer. This is one of the things that the humans have actually done right. You probably don't know it because it happened way before your time, but back in the 1970s, they realized that hairsprays and deodorants were using this things called CFCs, which was chlorofluorocarbons. It was a way to make them spray better. So your hairsprays and your antiperspirant would spray better. Well, those chlorofluorocarbons, these molecules, once you sprayed them into the air, would slowly filter up to the ozone layer. It takes 6 or 7 years, and then they started destroying the ozone. Back in the 70s, the scientists realized that, and they said, oh, this is really bad. If we destroy our ozone, we're going to have all kinds of cases of cancer and kind of change everything. So they banned the use of these CFCs. And so it didn't happen all at once because the United States and Europe, we banned them right away. And we said, because there were other molecules that they could use that weren't destructive. So they just switched over to the other molecules. But those cans and everything they produced, and it was actually in refrigerants like air conditioners and refrigerators, were still around in landfills emitting this gas. So they didn't really notice any change until about the 90s. Then they started seeing that the ozone layer actually was coming back. And so, yes, it did make a change. So what humans can do can actually affect the atmosphere for better or for worse. And so now the ozone layer is doing better. There's still a hole down over Antarctica, but that kind of occurs regularly. Good thing is, very few people live down there, so it's not as big a problem. When you get up here, notice you get to the mesosphere. So the temperature cools off here. It goes up a little bit because the ozone layer is absorbing that ultraviolet radiation, gets hot. And then it starts to cool off again. And it cools off as you go into space. And then it warms up a little bit again just because up here the molecules are very, very thin, but they're absorbing radiation and cosmic radiation and all kinds of stuff. So these individual molecules have energy. The ionosphere is because they're ions. The energy from the sun actually strips the electrons away. And it's up in this region up here is where we see auroras. Okay? Most meteors will burn up way up high like this too. So there's no real edge to the universe. But most people will say when you get above about 100 kilometers, you're essentially in space. But it just kind of fades out is what happens. That's about 60 miles straight up. If you're trying to set a record and say, I want to go to space, you really have to say you get 60 miles up before they consider it actually space. Otherwise, you're still on the Earth's atmosphere. All right. So that's the atmospheric layers. Make sure you know, we live in the troposphere. Okay? The ozone layer is between the stratosphere and mesosphere, right here. The water and weather all stays down here. And up here, the ionosphere is the edge of space. All right. Now, let's talk about the magnetosphere. We talked a little bit about this, but the Earth has its own magnetic field. And that magnetic field protects us from a lot of particles and things coming from the sun because they get funneled down through the magnetic field line